everyone. Welcome to our third morning session of the Popular interview questions and tips. Today we prepared 3 questions, but unfortunately the time I think will not be enough for all of them. So if you are willing to stay up to 12:30, I think we can make it work for 3 questions. Are you okay leaving at 12:30? No?
Let's just see how it goes and maybe.
Okay, so we will give you as little time as possible. So the first question will be presented by, Simon.
Okay. This question asks us if we can build this string from a given board. Basically, we have the 2-dimensional word and the word, find if the word exists in the grid. The word can be constructed from letters sequentially adjacent, where the adjacent cells are those horizontally and vertically neighboring. For example, for A, B, C, C, E, D, we can start from A, go up to B, C, C, E, D. So our function should return true. For example, for the second given C, we can build it using C, but this one we can do it A, B, C. Then we can't find any B, so we can't build it. So basically, just. Do you have any question?
Can you explain the C again?
C, you can start from this, go down, and do it. So basically,
can we go out to the 4 directions, right?
yes, you can go from a point to the any 4 direction. But if you go to this direction, you can take more.
And you can't use one letter more than once.
Yes, you can use
one cell more than once?
Yeah.
Yes.
Yeah.
Any question?
We can't use more than once.
Yes.
Oh, thank you. Once you get the idea, it may take some time for the implementation. So I think it would be enough to have a working solution on paper. That would be enough. So as to save time for the next questions, but try to come up with a working solution on paper. Implementing it.
Try to have.
Let's share that. We didn't want to take up time for implementation for this one. We have more important questions in the next slide. So what are you guys suggesting? What edge cases do you guys notice? Anyone?
If the length of the given word is greater than the given array length, then you have to return issues.
Okay, that is one kind of coding. If we are 2x2 board and if our word size is 5, and other edge case?
I give it as a graph traversal problem, and one weird part we can have multiple ways to go. For example, if our next letter is E, we can have this way E or this way E. So we have to handle that.
Okay. I think it's hard to accept that.
Yeah.
So how do they implement?
Explaining it?
Yeah, from there.
So basically, I keep an index of where the word is right now. So at the beginning, it starts from the index of 0, and I keep an index of where I'm currently on the board. So I start iterating over the board, and whenever I find the first element, the first letter of the word inside the board, then I start doing DFS from it. So each time I do DFS, I increment the index of the word by 1, and I check if the next word is available from the neighbors. And yeah, I look for B in this example, and if I can find B, and then I do DFS on that, and only if that DFS returns true, that means I just return true immediately then. I don't need to go any further, I just need to know that it exists. So if one of them returns true, I just return true. Otherwise though, I try to look for all the neighbors, and if none of them return true, then I just return false. And while doing that, I remove my current self from the visited array because it's going back, and it could be that place could be reached by a different path, and I want to allow that. So kind of similar with the unique path tree.
If we mark a cell as visited, and we may need that cell from another path, as you say, so we can actually use that cell, but if you mark it visited, we will not be able to get my travel. So what we should be careful about is we have to mark a cell visited, but when we return the back, it should be copied from the visited as or as Sagni implemented it, we changed the characters to some other character when we visit them, and when we get back, we can return to the original state.
Do we need to keep track of what the original state is?
When we reach B, for example, when we go to C, we mark B as
And we hold the
another
value of B?
character, maybe a number or something. But when we return back and use another path, we will make it the previous original character.
Already you hold the character up. They'll check the marks when it is.
Okay.
I'm inquiring searching for the word. The order market, after checking for the address symbol.
Actually, it doesn't matter. You do BFS, and if you reach the last index of the string, it means you have found all elements. Can we proceed? Thumbs up. The next question will be presented by Tumsa.
Actually, the title is longer than the description. It says number of operations to make network connected. You are given and other computers.
Use another marker.
What?
Use another marker.
The black one.
You are given in the computers. And you are also given their connections. And some connections are duplicated. You remove the duplicated connections to make every computers connected to each other. And you find there is a number of operations you need to perform on this. There is a number of connections you have to remove from the application one. For example, for this example, the computer with member is not connected with other computers, and these computers are connected each other with each other, and this connection is additional connections. So we can remove this one from this and add it over here, so that every computer is connected. In this case, you return 1. If you cannot make the computers connected, you return -1. You understand the question? Or you can proceed with the example.
This is the examples.
Let's say
The next examples.
Next examples. Number of operations.
so. Yeah, this one. We have 6 computers, and the computer with number 4 and the 5 are not connected with other computers. And here we have duplicated or more than we need connections. Here we have additional 2 connections here, and each computer should be connected to one another. Here, this one is what we are looking for. Again, we remove these two connections and add one over here, and the other one we add it here, so that every computer is connected. So we are removing two connections from this, and actually by removing two and make it on other computers and connected, we just need two connections, so our output should be two.
We'll take exactly one move. It doesn't matter which one we move. We can move this one here and this one here. Anyway, we can just create a connection between them. So basically, to connect two subcomponents, we need one move. So to connect n subcomponents, we basically need n minus one moves. For example, we have this big connected component, whatever, and another one, and another one here. We need to make something to make this, then another like this or this, whichever works. So basically what we're asked to do is find the number of connected subcomponents, then return n minus one, if this number of components is n. So basically a first question, afterwards the implementation. Is there anyone who didn't get it? Or anyone who wants to see the implementation?
For with demonstration. So after this code, let's see the code.
The other one,
Look.
Oh yeah, okay. Okay. Is there anyone with any questions regarding my approach? Oh, okay. All over again. The first observation is we need at least n minus 1. If the number of nodes n is the number of computers, we need at least n minus 1 to connect them, because in a connected graph we at least have n minus 1. And if we have less than n minus 1, we have to return, if it's less than n minus 1, then we have to return minus 1. Otherwise, the second observation is we have n minus 1 or greater, we can connect them because we have excess or enough, so it's okay. We can connect them. So if it's greater than n minus 1, there's number of moves we can make to make them connected. So after that observation, I thought of them as a graph, each computer being a node, and each connection basically being an edge. Then in this case we'd have on first X and this. So basically in this example we have one connected subgraph, another connected subgraph, and another connected subgraph. So here we're supposed to make this into one big connected graph. So we have to create a connection between this to this, from this also to this. So since we have the necessary amount of edges, we're not concerned with that. We can make it, we just want to make it efficient. Then, so that means we need a connection from here to here, and another connection maybe from here to here, or here to here. Basically, we need, if we have m, the number connected graph. As we said, n minus 1 here. To make this subgraph connected, we need m minus 1 moves. Same logic as for when we had n nodes, we need n minus 1 edges. When we have m nodes, basically if you're considering the whole subgraph as one node, this, and this, then we need m minus 1 edges. So the number of moves is the number of edges we make. So we just find the number of connected subcomponents, then deduct 1 from it.
So how did you find M?
To find M, basically what I did was I had, if I'm talking, you're speaking of implementation, right? Implementation was, in that case I had a set, a big visitor set. Then I go through every element, this element, I check if it's inside the set. If it's not inside the set, I do a DFS on it, and this same set is going to be passed to the DFS. So it goes to here, it adds it to the set, here adds it to the set, adds it to the set, and after I finish the DFS, it increments my counter by 1. Then it checks for this element, it's already inside my visitor, so it doesn't do anything. Same with this one, and it checks this again, it's not inside my visitor set, so it moves on to here. This is inside my visitor set, sorry. And checks here, since it wasn't covered by this DFS, this would not be my set, so would visit that, do a DFS on this, no other place to go. So this is added to our set, and our count increments by 1. Keeps doing this for this one, and basically our count is going to be M. That makes sense? Any more questions?
We are given an unsorted array of negatives and positives, all integers, and we are supposed to find the smallest missing positive integer. The smallest missing positive integer, and we have to do this with O1 time and On time and O1 extra space. Do you get the question? For example, if we don't have 1 in the array, the first missing positive integer is 1. If we have 1, 3, 4, the first missing positive integer is 2.
So are there going to be missing negative numbers? Should it matter?
For example, in this case, the answer would be 1, for example. If this was 1, the answer would be 5, right? We have 1, 2, 3, 4, 5. So find it with On time complexity and O1 extra space. This was a Google question. Element. It would be the length of the list size plus 1, right? If it included all numbers that are possible, the answer here would be 6. So the maximum answer from here would also be 6. But it might not be the case always. But 6 happens if all numbers from 1 to if all numbers are put in an ascending order from 1 up to the length of the list, right? So the maximum possible value we can find is length plus 1. This is the first observation. The minimum value we can find is 1, right? If the list doesn't contain 1, it's 1. If it contains 1, it will be 2, 3, or any other number. So, what we do we remember the approach we used to find duplicate numbers with On time? We can start from that end. Something. For example, if we have this number and if we are supposed to detect the duplicate number with O1 extra space, what we did was when we see 1, we mark 1 as negative, the zeros index. When we see 2, when we see 3, we mark the corresponding index as negative. In this case, it's a 0-based index, so we will mark the second index negative. When we see 2, we mark the corresponding.
You can't see 2, it's minus 2.
We always check the absolute value because the number given was from 1 up to n minus 1.
Okay, so your array might be minus 1, minus 2, minus 3, minus 4.
No, it was another.
Okay.
We want to start from here and eventually. So all numbers are positive, we are guaranteed, but not in this case. So we look for 3 and we mark 3 as negative, but 3 is already marked negative, so we can know that 3 was marked negative by another 3 earlier.
Right one is 3.
Yeah. So this is already negative, so we can return 3 as duplicate. In this question, we are guaranteed that the numbers are from 1 up to n minus 1, and there is only 1 duplicate. We can even find another duplicate with this approach.
Could you explain this again?
What we do basically is mark that index, keeping a visited hash set will take ON extra space. So instead of that, we keep the same, we use the same array, and we mark it's negative to mean it is visited. It's a way of keeping, if we have seen an element earlier or not. So when we see 1, we mark the zeroth index as negative, which means if it's negative, we mean it's visited already. And if we see another 1 over here, if we see 1, we come here to mark this element as negative, but it is marked negative already, which means
How do you
we
know
have
which index to go back?
from 1 to 6, it is from 1 up to n minus 1. The corresponding index would be 0 for 1, and 1 for 2, 3 for 4, go like that. Rest of it.
So in this case, we expect it to be sorted.
It doesn't have to.
You see the number, go that index mark.
When we see 4, we mark this one. When we see 2, we mark this one. When we see 2, we come here to mark this one, but it is already marked, which means we have another 2 before. So we see a slight difference from this one to this one. So what basically hinders us from making that number negative is it might be a negative number already. For example, we might not have 1 and minus 1, that would lead us to the impression that we have 1 already. So marking as negative would not work in this case, right? Because we have the negative values already. So do we need negative values? Do we have to consider negative values in this case? No, right? We can get rid of the negative values. But how? How should we do that? And do we really care about 8? Because the maximum possible value for this array is 6. So we don't need the 8 here, and if it is 12, we don't need to bother about 12 because it's already above the limit plus 1. Right?
So array size can go up to integer size, right? I asked you that. We can cheat like that.
Okay, let's finish. So we shouldn't bother about the negative numbers and for those numbers that are above the array size.
I think maybe we can make them 0.
But we want to take this approach and mark those indexes negative. So there is no negative 0, right? So we can not change them to 0.
I think you can make them 0, right?
In order to fix 0.
But if we make this 0, for example, and if we see 1 somewhere, we come here to mark it as negative.
Yeah, but if we need to do that, if we find that value to be 0, then we consider it as already valid, I guess.
But what if it is not?
But it's already if it was already a negative number before, then it's definitely not a duplicate of a different one.
But the problem is we need that value so that
Why would we
if
need the
we
negative
find
value?
some number and if that number's index
You will check from the beginning if the value is negative, we say, okay, this number is already visited. That is, for example, in the first index, if it's negative, we say, okay, 1 is already in the array.
Yeah, my point is, if it's 0, we can assume that like we can add
What if, for
another
example, if you
explanation.
have 2 minus 1 in different positions, and for example, when you get, for example, when you get to 1, you have to you have to change it to 0 as the first element.
No, I mean
So-
only the given negative numbers is what I mean.
Yeah, but what if the
we change
negative
the
numbers
negative
is?
numbers to 0 and if we consider all indexes with 0 value negative, we might get some trouble because if we see 0 here and if we don't have 1, when we see one, or
Or
we
you
see
have
one
to
is
do it
written
twice, for example.
after reading
You have to even you have to traverse twice to check that the numbers there is no negative numbers. So
Yeah, my
in
point
the
is,
first pass,
we're not gonna change the zeros when we try to mark them as zero. That's not what I mean.
it. Okay.
Like you just change the first negative ones from the given input, and then you just ignore them whenever you see a zero.
yeah, but you have to do it on the first pass, which means O of n. So n, you have to do it twice.
What's
I think.
wrong with that?
You have to do it all of n times, right?
Both twins
Twice
still counts as
is
over.
Okay, I think.
So you
I
mark
think, yeah,
zero
yeah. I think
as
that's
what?
will work.
As previous negatives.
Previous negatives.
Meaning,
Yeah.
if your index takes you to zero, then you can consider it as it took you to a positive number.
I
or
think it
something
will
like
work. Yeah, I think it will work.
that. It's just a suggestion. I don't know if it actually would work.
But if it is what we after marking those seen values as negative,
Not seen value. Okay.
what we try to do is if we first find a number that is not marked as negative, that is the least number, and we can return that index as the least possible positive integer that is missing.
And
And
this will return
after
zero.
marking all numbers as negative, if you have like -4, -3, and if this number is not marked, it means 1 was not found in this.
2.
Okay, 0 stands for 1, so 1 stands for 2. Yeah. So we can say that 2 was not found in this array. Because if 2 was there in the array, it would have marked this as negative. So in that case, when we see 0, we cannot draw any conclusion from it. Because we cannot mark 0. So what about marking them as large value as the array length is +1?
Yes. Array length can go up to integer maximum value, right?
Yeah. Or what about marking them as 1? You listen?
What?
What if we mark them as 1? As Murar said, if the array length exceed, if the array length is integer dot max value or the maximum possible integer value, if we change them to length +1, we face an integer overflow or something. If we add 1 to the maximum value.
I mean, it can go up to integer maximum value minus integer minimum value. And basically, I thought, okay, so if you mark all of them as 1, basically you say there is a 1 in this.
But in the meantime, while marking, what if we check if the positive 1 exists in the first place, and if it exists, and having duplicate 1s won't hurt. And if we don't find 1 in the process of marking them as 1, we can say 1 is not found, and so 1 is the answer, because the least possible answer is 1. If we mark
Oh,
all,
I see, I see.
if you mark all negative numbers as 1, and check if there is 1 in the array, if it is found, it wouldn't be a problem because many 1s and 1 1 has no changes in the whole array. And if 1 is not found in the array, it means 1 is the answer because 1 is the least possible missing number. Right? Is that clear? What if we for example, in this specific array, we change the negative numbers to 1. And while changing them to 1, we also check if 1 exists in the array. The real one, the positive one. So changing this to 1, 1 is still not found. Changing this, we don't change this one. We may change this one or we can leave it. It's because it's better than the array length +1. Let's change this one or leave it. We don't leave it. And 1 is not found. So we return 1 now? Because 1 is the least possible missing number.
Yeah.
And in this case, 1 is found. We change this to 1. To 1, we skip this. We have found 1, so 1 is not an answer, and having duplicates 1 has no problem in this case. right?
So, if one is not found, I mean, you have to look for two, right?
We will do that on the next part.
So, the W of n that is moved, it is like of, I mean,
It wouldn't be.
we are tracing after we are finding the minimum number that is. Why? Because, for example, if the array is 1, 2, 3, 4, 5, 6, 7, 8, the
I'm not checking for 1 first, 2 seconds, and 3 seconds. We're not doing that, but we want to make sure that every element in the array are positive numbers so that we can mark them negative whenever we find some value. Right? But is this making sense?
Yeah.
So we want to have all numbers as positive numbers, and we want to change them as positive, and to avoid contradictions, we mark them as 1, and in the meantime, we check if the real one exists. If it doesn't exist, we can immediately return 1. If it exists, and we have multiple 1s, and we'll go. So if this array changes to this kind of array, so we see 1, so we change the first index to -1. We see 1, we change the first index to -1. It's already marked. We see 3, we change the second index to negative. We see 8, it's above the length, so we have no base index, right? So we can leave it. We see 1, we mark it as negative, it's marked already. Then we can be sure that the numbers are marked correctly in this array. So the first unmarked number is the least possible number that is missing. So 0, 1, 2. So 2 is missing.
so we are considering
Zero
the index.
shouldn't be returned, right? Zero can't be returned.
So
did
we
you-
shifted the index.
So we're considering the index.
So we mark numbers as visited or not in the corresponding indexes. So after we mark all numbers, if we find the first number that is not marked, it means that number is missing, because if that number was in the array, it would have marked it in our first traversal.
Is there a case where the zeros stays unmarked?
What about changing zeros to 1 as well, as the negatives? Because we are looking for the missing positive numbers, right? We consider 0. Not positive. So let's run it through this example. We see 6, 2, 5, 9, 4, and we are changing it to 1. But in the meantime, we know that 1 is not in the array, so that we can return 1. But if 1 was in the array, think about like keeping a boolean if 1 is found or not, because 1 is the least possible number. For example, 6, 1, so 1 is found. So I can change any negative to 1. So 5, 9, -4, and I can change it, this -4 to 1. So I am sure that all numbers here are positive, right? So I can mark their corresponding indices to negative. So 6 is above, greater than the length of the array, so we skip 6. 1, we have seen 1, so we mark the first element, or the zeros index, as negative. We see 5, let's make this one 2. We see 2, and we mark the second index as negative. This negative means that 1 is found and 2 is found. And if 3 is found, we will mark this one as negative. So the first unmarked value is the least possible, the least missing positive index. So we see 9, we skip it. We see 1, we mark it here, it's already marked. So now all numbers are marked as negative through their indices. So if we see -6 here, it means 1 is found in the array. It has marked it as negative. When we see -1 here, we can say that 2 was in the array because only 2 can mark this index. And when we see 2 here, it is positive, which means 3 hasn't marked this element. So 3 is missing. Questions?
I mean, finding the number wouldn't take.
It takes all three n, which is one.
No, I'm not saying.
Why we are changing the negative numbers to 1 is we are sure that 1 is the least possible integer that can be returned, and if we found 1, having many ones has no problem, and if 1 is not found, we can immediately return 1 because 1 is missing.
So basically we are checking one's existence in the array with a boolean value, extra boolean value.
Yeah.
And the other ones started from the index 2, index 1. If the number is negative after the processing, it's seen in the array. If number is not negative, it is not seen in the array, so we return that value.
Yeah, the first positive one. The index of the first positive one.